Probably the first thing anybody did when they set out to embark on the first natural language processing task was to load some document into memory, some plain text file, and then split it into individual words, or as I should call them, tokens. That's pretty simple programmatically. It's mostly just split the string on spaces, a little bit more tricky to handle punctuation correctly. Popular words will appear many times, and that's great for doing statistics, asking questions like, how often do two words appear in the same sentence? Or as the TF-IDF algorithm would help us, what words in this document seem the most important? That they're frequent enough within the document, but they don't appear in every document. The is going to be frequent, we don't want that. Microprocessor will not be in every document. My GitHub username is my first and last name concatenated. Is my GitHub username going to be in your corpus? Probably not. So new words or rare words, these are problematic. If you have only a single instance of a token or zero instances, a new word, a word you haven't seen before, there's not much your typical statistical techniques can do when you have sparse rare data like that, or more so events you've never observed, new tokens. Yet the strange thing is, as human beings, we're actually pretty good at adapting to the presence of new words. Or I could pick a word at random, let's say squirrel, and start telling you all about it, but use my nonsense word instead of the proper word squirrel. You would quickly figure out, most likely, what I was actually referring to, and even if you don't get it exactly right, you inference a lot about what that word means based on context. And that's, of course, some of the promise of a lot of the advances that have come recently in natural language processing, that these word embeddings and sentence level embeddings, they're able to draw in some of that context. And that's very true, but they also do it on a sort of a token kind of basis. So one technique some listeners might know is character level embeddings. When a new word is invented, let's say computersaurus. All of you have some sense of what a computersaurus is. The compute prefix and the saurus postfix carry a lot of information with them. And that's not even the context, that's just the construction of the word. So these character level embeddings have gotten good at solving that aspect of the problem. But let's remember that these embedding vectors, they're pretty much black boxes. They're numeric representations that you would be hard pressed to explain in any interpretable way. Now, you can visualize them a little bit and things like that for sure. But for the most part, no. If you're going to work with embeddings, you're doing that to increase accuracy, not to increase interpretability. And herein highlights an interesting aspect of yet another reason why I think model interpretability is important. When you want your model to give you more than just the right answer, you want it to give you some metadata or something it's able to inference, some explanation, and perhaps some other details about what exactly this computersaurus might be capable of. Welcome to Data Skeptic Interpretability, a podcast previously focused on natural language processing, and now we're going to dabble in the interpretability of natural language processing. This week on the show, I've invited back returning guest Su Wang. In addition to the work we discussed last year on authorship attribution, today we're going to get into something, well, not entirely unrelated, but a brand new topic. Su is also a co-author on a paper called Distributional Modeling on a Diet, one-shot word learning from text only. It's a neat paper that not only delivers on the promises made in the title, but also gives us a unique insight into an especially interpretable way to solve the problem. All that right after the break. Thanks to this week's sponsor, the 2020 Gartner Data and Analytics Summit in Grapevine, Texas, March 23rd through 26th. Now is the time to act. You can save $350 with my early bird code. Those of you traveling on the company dime, keep in mind that your boss may have a budget for events and travel and this sort of thing, and if he or she doesn't use that up, they might lose it. The agenda has gone up on the web. 2 keynotes that caught my eye were Lee McMullen, speaking on creating a culture that is ready for AI, and Dr. Hannah Fry, who I love. She's on more or less all the time. I read one of her books. She's great. Professor, mathematician, author. That's just the tip of the iceberg across the 8 tracks they're offering. Visit gartner.com/US/data. That's Gartner, GARTNER.com/US/data. There, enter the discount code, all caps, no spaces, Data Skeptic.
My name is Su Wang. I'm currently a PhD student at the University of Texas at Austin. I'm graduating in a couple of months. Hopefully, I will be joining Google AI in July this year.
What's the nature of some of your work there? Do you have a sense of the kind of projects or at least areas of research you'll be focusing on?
I feel like I've been jumping all over the map even during my PhD. I started out with something and I'm doing something different now, which was a problem when I was writing my dissertation.
Well, what's your dissertation going to be about?
I've been looking at semantics in general. I started out with lexical semantics because that was the shared interest between my advisor and me. So this paper is from that era of my PhD. We're looking at lexical semantics, so we're trying to make models that are interpretable. So that was sort of one thing I was interested in. And I also did coherence modeling. If you are generating a story with a pre-trained language model, let's say, you tune it on some style, you generate a story. How do you make a coherent story such that on the discourse level, the story is interesting, makes sense, right? The participants and the events go together nicely. So that's the second subject I looked at. I also did a little bit of computer vision, specifically navigation. In many parts of the world, it's not like in the United States. People are not used to being given instructions like after 200 feet and turn left. People prefer to have landmark, what we call landmark based navigation. So when you see that CVS, turn left, that sort of thing. There was a team behind this to integrate the model's capacity to see the road, to have the visual input, and be able to give landmark based instructions in real time.
Well, that's exciting stuff. Paper I'd ask you to talk about is titled Distributional Modeling on a Diet One Shot Learning from Text Only. And while I think that's a great title that will be very explanatory to a lot of listeners, maybe to get going, we can break it down and highlight a couple of those terms. For example, do you have an intuitive notion or a definition of what is one shot learning?
In this particular context, we are trying to convey the idea of when you see a new word or new phrase you've never seen before, a human agent is able to guess what properties it might have just by looking at it in one sentence. That's sort of one exposure to that context. I have this example in my paper. So we found a cute, hairy wampum sleeping behind a tree. The wampum is a made up word which is phonotechnically English, never seen it before. So after seeing this one example, what can you say about wampum, what it is?
Yeah, I can think of a lot of stuff. It's an animal. I might even speculate it's a mammal. There's quite a bit from your sentence, actually.
That's the question we're interested in answering. How do you come up with all those things? You might even say, if I ask you, is it made of wood or is it made of water? You might say no. How do you know it's an animal, right? So that sort of questions.
And then the fact that it's a distributional modeling and also on a diet. Fill us in on there. What's distributed about it and what are we reducing with the diet property?
Well, on a diet, we meant that we only have this small amount of data. We are interested in finding out if this is all you got, how much can you get out of it efficiently? So that's what a distribution model on a diet meant. And a distribution model, so I mentioned a couple of sentences ago, we were trying to learn properties of these things. Wampum, an animal, that's a property, has four legs, that's a property, not made of metal, for example, is a property. Let's say that these are all properties. These are the things you don't see in an unstructured data set. It's sort of going back to the Gaussian maximum of information. People avoid to state the obvious. We believe using the distributional patterns, of context, how words collocate together in an unstructured corpus, it's possible to propagate that information. We're trying to take advantage of that distributional pattern to leverage the minimal amount of information we actually have.
I think some of the use cases are going to be fairly obvious, but maybe it's worth taking a moment and asking about them. With a model like this or tools like this, what are some either industry or academic applications that someone might put this to work with?
It started out as purely an academic interest. So we're learning these word representations using, neural networks these days, right? We have very rich information, very effective representations you learn from birds to contextualize using a large pre-trained language model. Those are effective, but there are questions these models cannot answer. Cognitively plausible representation, let's say for a concept like a dog. When you extract a 300-dimensional vector out of BERT to say that, well, that's the representation of dog. Why so? Because it's sort of close to these, other entities. They form a cluster in a semantic space that sort of defines it in a sort of distributional manner. kind of famous quote now by Firth in 1957 that the meaning of a word is looking at the company it keeps, right? You can say that, but if you're thinking about a concept like a category, a cognitive category, there are a lot of strange categories in the world we're not describing. I don't know if you know this book by George Lakoff, UC Berkeley. So he wrote this book in 1987, Women, Fire, and Dangerous Things. It's a weird title, right? Women, Fire, and Dangerous Things are in the same category in this Australian indigenous language called Durable. They're sort of marked linguistically as a category. When you say these words, you gotta put this specific prefix in front of them. I think it's a balang or something like that. How do you define those categories? What I was interested in was to characterize the semantic space. I prefer to look at it as a sort of multidimensional space where each dimension is meaningful. So Peter Gardenfors, this Swedish philosopher, he's quite influential in cognitive semantics. He was using this idea. What is a cognitive semantic space look like? What should it look like? It should be something like a Voronoi tessellation is the technical term. So this is a space where all the categories are these convex cells where you have your instances in there. Whenever you learn a new concept, all the instances in this cell adjust themselves. The distribution within the cell changes a little to tell you which instances are more prototypical. So that explains a lot of observations in psychology, like prototype. This sort of famous example is robin as a good example of a bird, better than a penguin. If your semantic space is something like that, have interpretable dimensions, and you have this sort of reasonable way to characterize it, better yet, you have a probabilistic structure behind it to tell you to model semantics properly. That would be an interesting route to go. An immediate downstream application, one sort of most immediate thing you can think of is when you ask the model to do something. Let's say you are translating from one language to a different language, and these two languages, let's say that they are taxonomically very distant. The speakers of these languages structure their cognition very differently. Well, this is sort of widely evidenced in cross-linguistic literature. When the model maps one linguistic structure to one structure in a different language, what this model is doing. How do you find out with a model with uninterpretable dimensions? If the dimensions are interpretable, it would be very interesting. This is how people see the world differently. English is my second language, right? Process of learning English, I found sort of learned many concepts that don't exist in Chinese, or sort of like one concept in English covers multiple concepts in Chinese. This sort of interesting cognitive mapping phenomenon. I think having the most basic structures like words, having an interpretable dimension, give us insight.
I'm curious to hear a little bit about the data sets you used in training. I know you'd mentioned that this is diet oriented. We want to see how much information we can get with a small data set, but how restricted do you make your learning?
Oh, of course. So we had a set of what they call feature norms. So these are words or concepts associated with human written property labels. Just call them properties. Some sort of labels for these concepts. We have 541 of those in the original data set. Aurelie Herbelot made an upgrade to the data set. So originally, all the properties were binary, right? You either have it or not. And now they're probabilistic in the updated version, which is the one that we used called quantitative McRae. The original data was called McRae. Now it's quantitative McRae. So a dog would have 100% chance to be an animal, probably 75% chance to have four legs because of possible unfortunate events. So you have these probabilities associated with these concepts. That was the data set we worked with. So this is a representative of what we thought of as human common sense knowledge with respect to lexical semantics, right? This kind of thing you don't see an unstructured corpus. Separately, we have a distributional corpus, which is a medium sized by the standard of then British National Corpus, which is our distributional corpus, where we wanted to take advantage of distributional patterns in there, sort of big data, to propagate the information stored in the 532 concepts, which are labeled. So those are the two data set that we used.
And then in terms of building out your model, are there any sort of feature engineering techniques or tokenization steps that you implement before really getting the ML pieces going?
Nothing special in particular, sort of typical thing you would imagine, right? It's getting rid of stop words and punctuations. Nothing particular in there.
Makes sense. Yeah. It's interesting. More and more that's been the trend I've found as new techniques and especially more and more compute has been available for NLP problems. That seems like a lot of these, maybe we'll call them older types of feature engineering techniques, have become less important as the corpora have grown. But even in your case, it sounds like they weren't a critical part in the step, which is interesting. Could you talk a little bit about the methodology and just in general how you start from those data sets to come up with your model?
So before that, I wanted to sort of give a sketch of the idea. The question is, how do you come up with that inference of Wampy Monk? It reiterated for the convenience of the reader. We were looking at the sentence. We found a cute, hairy Wampy Monk sleeping behind a tree as a human being. You guessed that Wampy Monk, which is a made-up word, nouns word, is an animal, maybe a mammal, and has four legs, all that sort of thing. We call properties. How do you come up with that inference? How do you do that? So the idea was we have a semantic space, the universe of concepts, let's call it. It has a probabilistic structure behind it. So when you see a new concept with partially observable properties, let's say that if in this instance we see that Wampy Monk collocated with hairy, cute, so these contexts give you some information about some of its properties, but you don't have a lot. Using the probabilistic structure in the semantic universe, you want to infer for the concept that's most likely to have generated this instance. You can imagine that there's a latent variable in the semantic universe that's associated with the concept that is probabilistic distribution, some sort of probabilistic model that generated this instance, which now you see is an animal, it has four legs, that sort of thing. What is involved in this process are two steps. First of all, in a text-only inference setting, you only see the sentence, right? You don't have an embodied learning. You don't have the privilege. You don't actually see the properties of the thing. You are learning the partially observable properties from contexts. And after that, you want to map it to some referent in your cognitive space. We're not claiming to make strong cognitive assumptions, but this is sort of how the idea came about. You are mapping this to potential referent, which by virtue of having seen these properties, you are able to infer for other properties. For example, it's an animal. What would an animal have? Probably four legs, probably having fur, probably not made of metal. That's the high level idea. Wanted to model this with hierarchical probabilistic model, which has a generative story. So the generative story is as follows. So a concept is a probabilistic distribution over a set of latent variables. In topic modeling, that's the model architecture we use. You can think of these as different perspectives from which you can look at a concept. From each topic is associated with two distributions. One is over properties. Is an animal, has four legs, these things. Another is over linguistic context in which it can appear. An example we saw, Wampy Monk is likely to be a noun that collocates with these words, hairy, cute, right? The context. So you have two distributions, one over property, one over context. When you generate an instance of a concept, let's say a dog, you first decide on a perspective from which you look at this instance, and then you draw some properties for it and draw some context in which it can appear, and you write it down. So that's the instance, the concept, the dog we observed. I'm assuming most of your listeners at least have some general understanding of what the topic model is. So from observed data points, you infer back to the parameters of this model, basically the posterior over the parameters. Wanted to understand the underlying, infer for the underlying distributions over properties and over contexts. So we have a generative model that looks like that. So the reason we have two distributions, properties and context, is because we want to link them together based on hypotheses we make about this sort of semantic space. So first hypothesis is in the distributional setting, knowing the co-occurrence pattern of context is helpful. If something is edible, if you ate something, that thing is probably, let's say, cookable. Co-occurrence of concept, the sort of similarity among concepts. Knowing that is useful. The other hypothesis is knowing the co-occurrence pattern of properties is helpful. You know that first you guess it's highly likely that this thing is an animal. Then what are some likely properties that co-occur with that property? So we have these two hypotheses. To model that, we want to have a joint distribution of context and properties. Once you have that joint distribution and you observe context, you'll be able to infer for properties. That's what the model does.
I'm wondering if you had any chance to look at how your approach would perform with ambiguity. For example, if I were to simplify your earlier example and say, we found a cute wampum and it had three legs. Is it a stool or is it an injured animal? I don't know. What sort of a behavior and inference can be
This
done
is the
under that
beauty of Bayesian
circumstance?
models, right? You see people integrating Bayesian techniques with neural networks with a single purpose of introducing uncertainty into the equation. Instead of giving a sort of deterministic prediction, you are predicting a distribution. When you see something that has properties that could be confusing, right? It has three legs, could be a stool, and it could be an animal too. There's your uncertainty there because we don't know the ground truth. The right answer is probably assigning some probability to one thing and some probability to the other thing. In the course of observing more contexts, wonky monk appears, the model is going to be better at getting the ground truth right.
One of the things that really stuck out for me about your paper was the Bayesian components and how that really gave you this level of interpretability we were referring to earlier. Could you compare and contrast that with what someone would get in a more black box model?
So there's been this recent paper by Dan Lee from US Army Research Lab. So they looked at the same problem, the mapping between distributional representation and a property representation, right? Previous work we compared to in our paper was Herbalat PLSR model, partially square regression, mapping from distributional space to basically word embeddings, as you know, to property vectors. This recent paper upgraded that to neural networks. You can see predictive performance is better there. And generally true that a generative model wouldn't outperform a discriminative model. This has been sort of empirically true.
Yeah, absolutely. I think the ability to then do something generative obviously depends on your use case, right? If this is just some web app or whatever, maybe it just goes for the highest accuracy. But in a more general setting, to me, the ability to get back that distribution and query it. Obviously, a lot of people might just want the argmax value. What do you think is the most likely context or property? But there are a lot of, I think, interesting decision theoretic ways to go with it where you're working under uncertainty, and not that many NLP models have that property. Was that something that you guys set out to do, or just came naturally with the fact that you were going to adopt some Bayesian approaches?
Our priority was interpretability and a proper way to model semantics, specifically inspired by Garden Force, this idea of conceptual space. So, of course, we found evidence in the literature where people try to make predictions better, mapping from one space to distributional space to property space accurately. What I learned from that was there's a learnable mapping between these two spaces. So, what I wanted to know was that sort of gave us evidence that it is legitimate for us to use distributional structure to propagate our property knowledge because there's a learnable map between these two. We weren't using it for its own sake. It was more like that was a convenient way, that was a more conceptually easy way for us to think about the problem.
Is there anything interesting to be said for how you computed the model? I know sometimes with Bayesian modeling in particular, if you have a nice conjugate prior, everything works out computationally, but other times there's a lot of simulations and stuff to run. How difficult was it to generate your model?
We have these two hypotheses, co-occurrence of contexts and co-occurrence of properties. These should be useful for the model. Based on those hypotheses, we constructed a set of models to test these hypotheses. We started out with two baselines. These baselines implement the model in a way that none of these hypotheses are implemented, right? So we don't make use of co-occurrence pattern between context and between properties. How we did this was as follows. In one of the examples, we were imagining a concept as a information giver in the form of a Bernoulli vector. You have these properties. Let's say we have 200 properties. Each property corresponds to a cell in this vector, and it's a Bernoulli with the probability. The context that give you that vector from which you can infer whatever appears in the context of this word should have these and these properties. If you see by selectional preference, what would be a concept that's selected by eat based on the fact that what can be eaten has these properties. We only look at this particular context and we don't make any connection between eat and cook and all the other words, just this context. How we did it was, manually label concepts sometimes. When you see a concept that is known, you use a count-based approach to update your probability or property vector. If you see, let's say, a cat, by label, we know cat is an animal. So we add one to the property animal. It has four legs, add one to the four legs. You take this counter-based approach to update this vector for this particular concept. After the update, we compute an expectation of that vector, you're turning it into a beta distribution, which is a conjugate prior Bernoulli, right? If you've seen this is an animal 99 out of 100 times, then it's 99%. The p would be 99. In that approach, we don't look at connections between contexts. That's how we got around these hypotheses. And the second type of model is where we implemented both hypotheses. We're modeling the joint distribution between contexts and the properties. So in the joint distribution, of course, everything is sort of connected in the model. We're implementing both hypotheses in this bi-model topic model, which is the one I described before. So this model basically links everything together, right? Implementing both hypotheses. And the third type of models we did was an ablation. Which hypothesis is more important? Or how much do they contribute? If you were to model the co-occurrence among contexts, how much performance gain do you get out of that? If you only model the co-occurrence among properties, how much gain do you get out of that? It's a standard practice. What we got out of that batch of model was these. Of course, we confirmed that taking advantage of these co-occurrence patterns, it's a large performance difference between those. And we also tested different types of contexts. Using dependency is more helpful. Having co-occurrence among contexts and properties both are useful. The last thing we learned out of that was, so there was this small data set called Animal, which is similar to quantitative McRae, the feature norm. So in quantitative McRae, you have sort of incomplete data. Let's say that sometimes people don't label everything. You just couldn't think of it. Like, for example, tortoise wasn't labeled as having four legs. It's on the sort of the labeling work was huge. And these new authors, Herbalot, she's a wonderfully creative. She did a new data set called Animal, which is that 72 animal concept, for which they designed a 54 dimension space properties, testing in a situation with complete information. Can the models do better? So we ran on that data set too. Basically, the same performance ranking was observed in this experiment on animal data set. We were able to get the mean average precision of this model to as high as 0.81 on animal. That's pretty damn good.
Given that this isn't some precision thing, it's language, right? And we're dealing with a small corpora. That's a very nice result, I would say.
With this project, we did have a few points to make. So one of the points was using information crowdsource of human. It is necessary because people don't say everything in text, right? You have this sort of incomplete information. That's one thing. The other thing is that learning from text only, it's not embodied learning. You are missing out on a lot. You're missing these different channels. I wanted to argue that this is absolutely necessary, and having the information, there's an interpretable way to learn word embeddings that is, from my perspective, more interesting than something like word to vec. There are things you can't learn. For example, if you have complete semantics in there, why can you not infer that the cat has four legs? It's going to be hard. And the other thing is that in my work on narrative coherence, what I found was the model. I was using GPT to tell stories. So we had this way to condition the content, to control the content of that story. Let's say that I want to make the story sad. I want to have different course of events happening. How do you get the model to tell stories? One mistake I see models make over and over again, even with a common sense knowledge input, was this. In one story I remember was this person, John, hates this woman, Shay, so much. He did a lot of things to express his hate of Shay. And then the last sentence was, John was furious and dated her for years. So what's wrong with that? Like, what's the problem in there? I feel like for all the participants in a story, if you know the properties of these entities and you know the properties of these events, it's going to be way easier for us to characterize the concept of coherence. But currently we cannot, corrupt text in some way and use a bird to classify. And that's one way to do it, but we don't know how it does it and still make some mistakes. And recently people found that Roberta is better than Bird in making common sense inferences, but we still don't know why. What we would argue was if you, on the sort of level of words, if you could make things more interpretable, it's going to cascade into more interpretability on downstream applications like that. That's one point we wanted to make. The other thing is we want to sort of give a disclaimer that we don't want to say that this is absolutely cognitively correct, because there are cases we don't model, especially cross-linguistically. Like the one example I gave you at the beginning of this interview was Lakoff's women, fire, and dangerous things falling into the same category. These are the things he calls radial categories. categories, right? Things are connected by arbitrary means. For example, woman is also in the same category with sun and sunscreen. So how are they connected? Women by religion was linked to sun. And in sun, you can get sunburn. If you get sunburn, you need sunscreen. So this sort of connections also form categories. So we aren't able to learn those. Still trying to figure that one out.
Well, to wind up, where can people follow you online?
I have a personal website, which you can include it in the description, I guess.
I'll have it in the show notes then for everybody. But yeah, Su, thank you again so much for coming on and sharing your work.
Thank you for inviting me.
Thanks for listening to Data Skeptic. Our guest today was Su Wang. Check out his homepage at suwangcompiling.com. Link in the show notes. Our theme song is Number 5 by Big D and the Kids Table. Claudia Armbruster is our associate producer. Vanessa Burciaga is our guest coordinator. I've been your host, Kyle Polich. Thanks for listening.